Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at one of our newest products, the TI Innovator Hub, and how it can connect to different STEM projects in your classroom. I see that many of you are joining us for the first time, so we'd like to offer a special welcome if this is your first T-Cubed Professional Development webinar. We'd also like to thank everyone for completing the live survey on the right side of your screen. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm super excited to introduce our two panelists for tonight, Stacy Thibodeau and Fred Foch. Stacy holds Bachelor's of Science in Biology and Chemistry and a master's degree in Educational Leadership from the University of Louisiana at Lafayette. She has been in the science classroom for 17 years and currently teaches at David Thibodeau STEM Magnet Academy, also in Lafayette, where she teaches Chemistry 1, Anatomy and Physiology, and also Biology 2 AP. She has also taught biomedical science courses in Project Lead the Way program and Chemistry 2 AP. She uses TI technology to assist her teaching, data collection, and modeling math concepts, linking them to science content. Stacy, thanks so much for being with us tonight.
Yeah, good evening. Thank you for having me. I'm happy to be here.
And Fred holds bachelor's and master's degrees in chemistry from Missouri State University and taught for 27 years at Glendale High School and Drury University. He taught a variety of classes during his tenure, including STEM, AP Chemistry, Organic Chemistry, and AP Physics. Fred currently is working in the Product Development Division of Texas Instruments, where he is able to develop technology to be used in math and science classrooms. Fred, thanks so much for joining us tonight. We're expecting a large crowd, so your audio is muted. Feel free to send any questions to Fred or Stacy using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. This session is being recorded, and as a reminder, we'll provide a link to the event certificate of attendance at the conclusion of the webinar. Once that recording is available, we'd love for you to follow along with that recording. That way you can go at your own pace. We also hope you don't have any audio issues tonight, but in the event that you do, try looking in the participants window where your name is listed, and in the lower left-hand corner of that little window, there's a little phone icon. If you click that phone icon, if you're having audio issues, it'll allow you to call in using your phone, which should deal with any potential audio issues that you may have with the audio broadcast. At this point, Fred is going to discuss our agenda. Fred? Fred, just so you know, you may be muted. Fred, you're definitely muted on WebEx now. I just saw the red microphone come up.
Okay. Can you hear me
now? There we go. Yep.
Great. Sorry about that. Tonight we have a good lineup. We're going to talk a little bit about the Innovator System, what it is, how it fits into STEM education. Also going to talk about all the wonderful online resources available to teachers. We're going to see an example of one of the online resources at the STEM projects that Stacy has used with her students in her classroom. We're also going to take a look at some of the future STEM projects for the Innovator that we're trying to develop. And then I believe that you're going to talk a little bit about a webinar giveaway.
Absolutely. We're excited about it.
Good deal.
And Stacy is going to discuss our expected outcomes.
So tonight we hope that we'll be able to have students to synthesize, build, and understand unique projects based on their own creations. We also hope to provide an overview of the 6 skill builders in the Path to STEM projects arena, and also to create excitement within your own classroom using the TI Innovator Hub with the TI LaunchPad Board.
Thanks, Stacy. Fred, I'm turning it over to you, and you can go ahead and share your desktop.
Thanks, Mike. So tonight, what I would like to share with everyone a little bit about the TI Innovator Hub and a little bit about what its ideal is. As Mike mentioned, I was a teacher for 27 years and was very interested in bringing STEM education into my classroom. And now I have the good fortune of working with many teachers to try to figure out what a good STEM project looks like. We certainly don't have the answers, but we like to listen to teachers and get ideas of what good STEM projects are. And so we've tried to develop a tool that will facilitate that, and the TI Innovator Hub is that tool. So I'd like to share with you a brief overview of that tool. The Innovator Hub is made from a Texas Instruments LaunchPad. This is a board that is used by engineers to develop new products based upon Texas Instruments chips. We wanted to have this as a tool for students to use in the classroom, but felt like we needed to make it ready for the classroom. So to do that, it was placed in a durable enclosure that can be dropped and handled a little roughly by our students because we know they're not always the most gentle with equipment. And we also try to kind of electrically harden it so that mistakes can be made without threatening the equipment. And we also added some features that allow connection to the LaunchPad board with what are called Grove sensors and actuators, which I'm going to show you a little bit about here. And those go into the 3 input ports that the Innovator has and also the 3 output ports. In addition, there's kind of a low-level breadboard access to the Innovator, as well as an I2C port that will be used for upcoming products. In addition, there are built-in devices that are on the Innovator for out-of-the-box experiences with coding and science exploration. There are LEDs, one of which is a red, green, blue LED that can be mixed with colors, and there's a speaker for exploring different frequencies and interactions among sounds, and then there's also a sensor that detects the brightness of light in the classroom. So out of the box, a teacher can get involved with using the Innovator as a tool for doing STEM activities and using the tool to do some NGSS engineering design ideals. So the way that the device works is it hooks into a calculator, a TI-Nspire CX, or a TI-84 Plus CE. Either one of these has a USB port that can connect to the Innovator device, and then built into the operating system of the calculator itself is a programming language, TI Basic, that can be used to write programs to control the Innovator Hub. So no computer is needed to take control of the device, and a program can be written on the Nspire and then run in real time on the Innovator, and this can be used to design STEM projects that your students can do in the classroom. In addition to using the TI Basic programming language with the Innovator, there's also a built-in Lua language that people who are interested in developing content for their classroom can write in. And in addition, at Texas Instruments, we've written a few activities that allow teachers to explore some of the big ideas in physical science and in life science that are just out of the box, ready to go activities. Some of the sensors that can be plugged into the Innovator are input devices where we are measuring things like temperature, motion from an infrared body heat, soil moisture. This is an example of an output device turning a LED on. This is an input device, a slider. There's a device, there are input sensors that can measure the loudness of a sound or the brightness of a room. You can connect a submersible water pump up. There are power control units, little motors, relays for controlling motors or lamps or that type of thing, little haptic vibration motors, temperature sensors, and these are all inexpensive sensors that can be built into projects. Use a little hot glue to fasten them in place, and don't have to worry about them being a big budget item. Most of these go for about $4 or $5. The way that a teacher can get started with all of this is through 10 Minutes of Code. 10 Minutes of Code is a online resource that I'm going to show to you here in just a bit that gets students started coding on any TI graphing technology that they may own. So it doesn't have to be a CX or a CE. Any graphing calculator will allow students to begin exploring coding. And in 10 Minutes of Code, students write programs that are very short and to the point that ideally take about 10 minutes, so they could be kind of a little bell ringer type of thing that allows them to get some hands-on experience with some of the big ideas in coding, that is editing programs, running programs, using control, conditional statements, and variables, that sort of thing. There are all sorts of student and teacher documents associated with this line of activities, and a teacher can simply download those for free and get started using those in their classroom with just the technology that they may already have in the classroom. We hear from teachers quite a lot that they're interested in bringing coding into the science classroom. It's a good NGSS content or NGSS practice, an engineering practice, and it's a way that science teachers can bring it into their classroom if they choose to do so. In addition, there's 10 Minutes of Code with the TI Innovator Hub, and here if the classroom has Innovator Hubs available, they can plug those in and students can have an experience with something called physical computing, that is writing code that actually does something in the world around it, like, for example, turn on a light or turn on a motor or detect the temperature within the room and make a decision based upon that. And so 10 Minutes of Code with the Innovator is an opportunity to get students started programming with actual hardware devices. Good introduction to robotics if you have a robotics club or if you have a STEM camp in the summertime and you're wanting to do some activities in there that have some engineering and some science and of course math. This is a great opportunity for that. There's also these pre-authored lessons that I described earlier that have already been written in Lua. These are very polished activities that students can learn about some of the big ideas in physical science and life science using the TI Innovator. They do build along with these activities. So there's a task that they have to solve, and they have to design and build an apparatus to solve that problem that they're tasked with, and then they can use the software that's on the Innovator to control that project, and then also get some interactive feedback to help learn those big ideas. Tonight, we're going to be taking a look at the Path to STEM projects, and this is a line of about 6 units, and each unit has 2 activities. One of the 2 activities is called the Skill Builder, where the students learn some basic idea that is central to physical computing, that is computing using something like the Innovator. Things like, how do I get information from the real world into a program, or how do I take calculated output from a program and then do something with that in the world around us by turning a pump on or turning a motor on or turning a light on, that type of thing. We're finding that this is an area that teachers are beginning to be interested in as we start to talk about STEM. And the Path to STEM projects, again, are 6 units that give the students the skills needed to be able to synthesize creative projects on their own. It'd be a good opportunity for a student who's interested in, say, a science fair project to do this as kind of background knowledge. Then they could use the Innovator as a tool in a science fair project. These would be great for a STEM camp or a robotics club, that type of thing. And Stacy is going to share with us some of her experiences of using some of these projects in her classroom. And I'm eager to hear how she's implemented them and to try to learn from her experiences. As I mentioned, at TI, we know that STEM is important. The Texas Instruments has a vested interest in making sure that there's a pipeline of well-educated STEM students. And we want to try to offer tools to facilitate STEM education through project-based learning. Again, we are very interested in hearing from teachers to hear how they can use this tool to do some STEM projects. And so hopefully the path will help us to get some of those skills to get somebody started in our classroom. So now to get started with all this, how are we going to get started with all this? Well, if tonight we're talking about the 84 plus CE. However, this is also, you can do all of this with the TI-Nspire. Either technology will work, but since we have kind of chosen the 84 to work with tonight, I'm going to point you to some of the details there, but everything that you hear for the 84 would apply also to the Nspire. So one of the first things that you want to do is to make sure that you're up to date with your operating system. As changes are made to the operating system to give new utilities to the calculator, this is where you're going to go to update that. I'm at education.ti.com. All the things that I'm going to show you are located there at education.ti.com. And I'm simply under the operating system tab for 84. And right here, you can see that you can download and upload that to your calculator, the new operating system. In addition to the many different apps that are available, you can also see right in here is the Hub app. The Hub app is an app that is loaded onto the calculator, and it's separate from the OS so that it can be modified as we add functionality to the Hub. And so periodically, you'll want to make sure that you have the latest version, and that version is right here on the website, and you can see it also when you run the program. So that's one of the things that I wanted to show you was the update of your operating system. And then the next thing is to make sure that your hub is also updated. And so these are things that if you have recently purchased your equipment, they are up to date. But as with all technology, keeping the software and the operating systems up to date is important. And so for the Sketch, which is actually software that runs on the Innovator itself, there's also a process for updating it. This is not something that I anticipate you'll be doing too often, but it's one that you'll want to check on periodically to make sure that you're up to date, particularly if new tools come out that you want to take advantage of. The next thing that I wanted to share with you is the breadboard kit. When Stacy does her work with her students, she's using this kit right here, the TI-Innovator breadboard pack. And inside of this, you'll find all of the parts that she's going to be referring to, and those are listed here. In addition to the breadboard pack, there's also an I/O module pack that has some of those Grove modules that I referenced earlier in my PowerPoint already prepackaged. And then you can also get some other items to go with your Innovator. And then lastly, I wanted to show you the website for the Path to STEM projects. Again, this is from the education.ti.com website. And on here, you'll be able to download all of the files for each one of the units. And so each unit has a project as well as a skill builder. Tonight, we're going to be looking at Unit 3. Setting analog output is kind of one of those fundamental skills for physical computing or using the Innovator. And there's also a video here that we're going to talk a little bit about later and take a look at that shows you how to do some of the build. And then there's a project after you've completed the skill builder. So in all, there are 12 activities here. And this is enough for an entire camp, a STEM camp in the summertime, or if you have some time after one of your high-stakes exams and you want to bring some of this into your classroom, this is a good starting point. Or if you have a robotics club and they're trying to get at kind of the fundamentals of how robots work, these are all the fundamental ideas that are in something like a robotics competition. And so now I'm going to go ahead and turn this back over to Stacy, and she's going to share with us some of the great work that she's done in her classroom with Unit 3. So Stacy, I'm eager to hear all that you've done, and I'm going to hand it over to you.
All right, thanks, Fred. So hopefully you have now an idea and a vision of what TI wants as far as where the company is headed with the entire Innovator and how it's going to fit into STEM. One thing Fred mentioned earlier is that from the website you can download all of the activities. So what I have, and I'm going to come back to them, these are the student activity guides. This is for Unit 3 Skill Builder, like he said. And so what we're looking at, this is the student guide, and then there's a teacher notes. And for me, that was big because when I started with this, I was like, hey, that looks like something cool I would like to do with my students. But at the same time, I'm a chemistry, biology, life science teacher and have very little background in physics. And so I was extremely overwhelmed with this. But the ease of walking into this wasn't extremely overwhelming. And then just like with any TI product, and you add a sensor here or there, the kids are the ones who actually have taught me a whole lot. So this presentation will be shared with you, like Mike was talking about earlier. At the end of the presentation, at the WebEx, you'll have access to it. That way you can follow along at your leisure. I am just very methodical when I do this with my students, so I kind of did that tonight, and you'll have this when we're finished. So when I started with this, I was like, this is really cool, but, right? So we all have standards we have to address. We all have accountability, those of us that are in the math or science classrooms, and so what do we do? And so I found this, this slide, and I really enjoyed being able to see the practices for math and science. ELA pulls in as well, but what does that mean for me as a classroom teacher? Well, if I'm the science teacher, that's what I do, I am going to ask questions always. Sometimes it's me, sometimes it's the students that want to ask questions. Or, this is the big one for us now, especially if you're in either an NGSS state or if you're an NGSS-like state, which Louisiana is turning into one. We have this whole engineering science and engineering practices. And so what's the problem? We have to use some kind of model. We have to reason, appropriate tools. We want to engage in argument. We want to make use of structure. And so really and truly, we can put Common Core standards, make sense of problems, and NGS says ask questions and define. Common Core says we need to reason abstractly, and NGS says we use math. And so both of them together can be done in any of the math or science classrooms, but with TI and TI technology, we can actually accomplish this. My TI journey started in 2013 when I was first introduced to the Nspire, and I haven't turned back. I embrace everything that TI comes out with. I plan my lessons around TI technology, what I have in my classroom. I grant to get more stuff because they truly embrace what is meant for that thread between the math and science. You can't have science without math, and you can't have math without science. And so that STEM and engineering design is where we're headed with NGSS. And so I've worked with some teachers, mostly in my district and my state, talking to a few on blogs and different forums. And a lot of teachers are scared. They're scared because engineering to them is something that people do who are smarter than them, and they're very intimidated. But we do the engineering process in the science classroom all the time. We just don't necessarily have a build that's always associated with it. We ask problems, and based on our problems or our experiments, what are our constraints, what are our limitations? Then we come up with ideas, or we do some kind of research. I know teachers have seen different engineering design process models. This was one that I like and I have in my classroom. I do teach at a STEM magnet school, and so we focus on the engineering design process in all of our courses, even ELA, even PE, and we try to incorporate that across the board. But it's not just, hey, this is what some civil engineer is going to do. We can use the engineering process daily. So what I'm going to kind of jump back and forth. I kind of have a few things. One thing that I want to make sure that we talk about is what we are doing, all right? So the first couple of units in the Path to STEM project looks at digital, either input or output. Digital input and output is finite. It's either on or if it's off. And when the handheld or the calculator interprets that, the Innovator and handheld, they interpret it as a 0 or a 1. So that's the light switch is on or the light switch is off. And it's considered to be counting as far as the units. When we're looking at analog, which is what we're going to do today, that's infinite. We're using a measurement. And so I found an example earlier when I was trying to figure this out to explain to my students is what's the difference? Okay, so think of a clock, an old-time grandfather clock that has the second hand, the minute hand, the hour hand, and we have lots and lots and lots of time measurements within there. That would be like analog, where it's still 3:15, but it's 3:15 maybe and 32 seconds. Most of our digital clocks, though, give us an exact measurement or exact number for the time. Most of our digital clocks don't necessarily have the seconds that's going with it. And so we have one number. So that's kind of, I guess, my way of explaining it to students, digital versus analog. And then when we're looking at what we can do with each, whether we're sending message to the innovator and telling the innovator to do, or we're receiving message from the innovator and telling the innovator what happened, that's going to be input versus output. So if I want to send a message to the innovator and say, go do this, I would get something, right? An input would be I'm receiving a message from the innovator that says, hey, this happened and I want you to tell me what happened. And so when we're doing input on the innovator, we're using analog input. Our Innovator Hub uses what's called a 14-bit in its values. And so we're going to have lots and lots of numbers that thankfully the calculator is actually going to interpret that for us. Imagine if we had to do that by ourselves. I think that would be pretty difficult. So what we're going to do tonight is using what's called a potentiometer that has a knob on it. And so when I first introduced this to my students, they were like, wow, this is like anytime you turn a knob. So on a radio, or if you're turning on the hot plates like in our classroom, anytime there is a knob that's changing the input into the system. So I'm changing the amount of energy that I'm allowing into the system. So it's voltage, meaning it's energy coming into that system, and then I can change how much I'm actually applying. So with digital, it's either all or nothing, like I was explaining. With the analog, I can say, maybe I just want a little bit. So I want to turn that hot plate on, but I don't want it at 10 where all of the energy is coming to the hot plate. I just want to turn it on to 1 because I want a slow water boil. Or I want the stereo on, but I don't want it full blast. I just want a little bit of music because I'm going to bed. And so we're going to have to do something with this data that's coming in. That's these big old numbers from 0 to 16,000. So there's going to be some math in there. When we use the Innovator is has its own power supply to it. I'm going to show you a picture of this that's bigger in a second. So this is one of the top or bottom looks of the Innovator. The top row has 10 sections in it, and there are certain ones that are set for different, whether it's digital or analog. And the bottom has some grounds. It also has a 3.3 volt, which you're just using the energy from the Innovator and the calculator. And then there's a 5 volt that you could plug into and have an external battery source. We're just going to use tonight just the 3.3 volt. So the maximum amount of voltage that could possibly pass through this would be 3.3, but we want to change it. We want to change the amount of voltage, which is cool, but at the same time, what does that mean? What is those numbers that are coming in if I were trying to do this like a radio? So what does a voltage of 3.3 mean for the level of intensity of my radio? So you will have access to this. So the first thing you're going to do is everything on the programming of the Innovator with either the 84Cs or the Nspires. I'm an Nspire girl. When I started with TI, I started with Nspires. Let me take that back. When I started with TI, I was in college, and I think I had a 81 or an 83. But as a teacher, when I started with Nspires, when I started with TI, I started with Nspires. And then when this Innovator came out, I was like, how cool is this? Like, I can use it with either, depending on what my students come to me with. I'm very fortunate that the school that I'm at, we're an entire Nspire school that we're a 6th through 12th grade school, and we start with Nspires at the 7th grade. But I don't know, I may go to a new school and we have 84. So this is program written on the 84. It is all menu driven, like Fred was saying. You don't need a computer. You don't need this fancy language that kids have to memorize. It's that great intro for students that are either interested in robotics or they're interested in programming and don't necessarily know where to start. I started a STEM club at my school. Even though we're a complete STEM school, I had some students that weren't getting the programming that they wanted because they weren't part of the robotics team, because they were athletes or not necessarily wanted to be on robotics. And so that's what I started with them. I first started with the TI codes that Fred mentioned earlier. We did the coding, then we did the Innovator coding, and then we came into the projects. I probably got through Unit 2, and they were like, okay, turn this loose. We want to try this. What does this do if I insert it? So it was almost like when I started with the data collection devices, turning them loose, they want to know more. So again, this is all menu driven. On the handheld, there's a program key, and the program key has all of the menus. And so we're going to call this program voltage. We're going to create a new program, and then we're going to have to connect the calculator and the Innovator. We have to explain to them the two devices what we're doing. So we're going to under program there is a hub menu that is the number 8, and we're going to send connect input. And our input tonight is analog in. So we're going to connect the analog device, whatever it is. Tonight we're going to have a potentiometer, but it could be different ones. We're going to connect analog in, and we only have one of them. And we're going to connect it to what's called BB5. BB5 is one of those that I talked about on the back of the back of the Innovator, BB 5, 6, and 7, I think, or 4, 5, and 6 are designated for the analogs. So we're going to connect it specifically to the BB 5. And so that, again, we're just saying, hey, go connect, right? So send the message to connect analog 1 to BB 5 port. And then I'm going to set a range, and my range has to do with the values that the analog is going to be reading. And so we selected from 1 to 200, and we're going to give it an actual name. And so I connected, I set an in. So it's like the in value is a file cabinet that I'm going to open up and put all my data in, right? Okay, so I have the file cabinet of where I want to store my papers. Now I have to tell the calculator to connect back and read what that measurement is. And so it's going to read analog 1, whatever analog 1 is reading. And analog 1 for us, like I said, is going to be our potentiometer. So it's going to read it, but I have to tell it, hey, report back to me, right? I have to send the message back to the calculator, so I'm going to tell it to get that information, and I want you to tell me what it is. Analog is this. And so when we run the program, it will display, DISP tells me to display, and so it will display analog equals whatever the value was that was received by the Innovator. Now this is where I was talking about, we're going to get all these numbers, okay? So if you've ever done data collection and you have that sensor and you've put the sensor in, let's say it's a temperature sensor and you put it in hot water and it reads 101. Well, what does 101 really mean? 101 really means somebody somewhere took the numbers that come from the sensor and made it make sense to us. And so we're getting raw, that 14-bit raw analog input from the Innovator to the calculator, and it doesn't mean anything to us. So we have to convert it into the voltage numbers. And so we're going to use our 14-bit, so 2 to the 14th. There's some physics that's involved in here. I'll show you in a second what we're actually doing. And it's going to display our voltage. We're going to wait a little while, and we're going to end. So basically, really short program. Not a whole lot of steps. You send to say, hey, go connect. I want you to set this up. Then I want you to read it. I want you to get the information. I want you to display it. But, hey, I need to do a calculation in there. I need to spend a little bit of more time maybe with the calculation part with students to make them understand what's going on. So what did we just do? Well, what we have is a voltage divider, all right? And so we have voltage in, we have input, we have that 3.3 volts coming in from the Innovator. And by having, if you imagine this being my knob, if it's closed, I have a specific reading. This is my voltage out. And as I open it up, it's allowing more and more of that energy to flow from Vin, which is my 3.3, passing through resistors. And I tell my students a resistor, I think of a resistor like as a funnel. It's a funnel that only allows certain energy through it at a certain time. And so as I open up my my knob or turn my knob, I'm allowing more and more energy to flow through. And so the way it's set up, which is, I know it's you just really have to walk through it. So this is my connection to my ground. The red is my connection to my actual energy coming in, and the yellow is the connection through the knob. And so as I turn it, I'm going to allow more and more energy through, and the yellow will read the energy coming through. So this is exactly what we just said a while ago. It is my speaker, it is my volume on my radio that says no energy, so I don't get any sound coming through my speakers. I turn it, it gets louder and louder and louder because more and more energy is coming through. So also in the presentation that you'll get, it walks you through the actual design. Again, I'm a classroom teacher. I need step-by-step with my students, and I also need to make sure when I'm setting this up that I have everything. And so Fred was mentioning the Innovator with the breadboard pack. Excuse me. And so this is on my kitchen table taking pictures. And so the potentiometer actually has 3 legs on it. When you are setting up breadboards, breadboards are cool because they allow you the ability to move things around without having to solder or make anything permanent. So you want to add a potentiometer to a project today. Tomorrow you can take it off, put it back in your box, and add something else on tomorrow. It explains circuitry without having to solder and do permanent circuits for this. So when you're working with this, you have columns and rows, and I apologize that it's very small. The columns are electrically connected. So anything that is going up and down in the same area is electrically connected. So you're actually going to plug wires from the Innovator to the columns, as exactly like the description says. So you're going to end up with 1 wire from the potentiometer to this little bus area, the breadboard bus area, to the ground of the Innovator. Then you're going to take a different color wire and the other leg to the bus, then to the 3.3 volts. And so you have the same connection that we were looking at in the schematic earlier. And so here's my potentiometer. I have my knob that I can turn, and as I turn it, a certain voltage is allowed to go through it. So again, this will come to you when you are finished with the actual WebEx. I do want to show you a video. The videos are online. It also walks you through everything that I just talked about.
In this video, I'll show you how to build a circuit, connect it to an analog input pin, and program it to calculate and display voltage that is controlled by a potentiometer. Please refer to the Unit 4 Skill Builder teacher notes for detailed instructions. First, let's go over the technology. You'll need your Texas Instruments graphing calculator and a TI-Innovator Hub with TI LaunchPad Board and its Mini-A, Mini-B USB cable. You'll also need these components from a TI-Innovator breadboard pack. The TI-Innovator breadboard, yellow, black, and red male-to-male jumper cables. Separate them from the bundle that came in the pack. The potentiometer with knob. Start by placing the potentiometer in the breadboard and connecting its middle leg to the BB5 analog input on the TI-Innovator Hub. Use a black cable to connect the left leg to the blue bus and connect the right leg to the red bus with a red cable. Connect the breadboard red bus to the 3.3 volt pin on the TI-Innovator Hub with a red cable. To complete the build, use a black cable to connect the blue bus to a ground pin on the TI-Innovator Hub. Connect the TI-Innovator Hub to your TI graphing calculator. Insert the A end of the connector cable into the calculator and plug the B end into the TI-Innovator Hub. Now you're ready to program it to calculate the voltage that is controlled by the potentiometer and display it on the handheld. To help you get started, there's a sample program in your teacher notes for this skill builder. Once your students have completed this activity, they're ready to apply what they've learned for the Unit 4 project, How Clean is the Water?
So the video is there for you after this WebEx that you can actually go back and see. The presentation is there. That way you can see, excuse me, step by step. And then what the guy in the video, Eric, was talking about is where I actually ended up with my students. So like I said, I teach chemistry, and so why would I use this in my chemistry classroom, right? And so within the project, we actually build our own conductivity meter. And so how cool is that, right? And so my students learn about conductivity, we learn about changing solution concentrations, and then what's the difference between covalent solutions versus ionic solutions. Well, then now it's no longer just here is a conductivity sensor and we plug it in and this is what it means. we then create our own conductivity sensor, and then they learn about circuitry, they learn about programming, they learn a whole lot more about conductivity, and there's also an extension to this. I actually gave them standard concentrations of sodium chloride solutions, which is table salt, to those that don't know what sodium chloride is, just joking. And then we did an unknown, and so I just gave them a concentration that they had no idea. And so we broke out our Nspires, we graphed a standard curve, we then plotted the point of what our unknown solution was and extrapolated the data to find out the concentration of our unknown solution. Again, so not only did we do the STEM as far as the engineering design, the building of the conductivity meter, we did some coding, all of that, we then analyzed some data, which is another way to bring STEM into your classroom, is that they were given the opportunity for an unknown solution and then had to use real-world situations. So why is this important? Well, it's important for us because most people don't drink dirty water. We're not drinking water that comes from a stream that we can clearly see is not safe to drink. But what does a clear solution? It may have impurities in it, or it has high levels of salt that we might not necessarily want to drink. So again, bringing this into a real-world situation, that students were able to bring that entire STEM concept to life. So were there questions for me that maybe anyone had a specific question for me?
Yeah, we actually had a question earlier from Pleasant View School, and they're wondering, like, what's the time frame for how long this might take in your classroom? For instance, like, how long would it take your student, Stacy, to go through this project?
So for this activity, we actually did a couple of the 10 minutes, 15 minutes here or there. We had students that were out for this field trip, and I did the 10 minutes of code for the innovator with the Nspires. Really just fun. I told the students that I wanted to expose them to things that they were never exposed to, and we started with the coding back in the fall when I first got my hands on the innovators. And then that led to questions. My students want to build every sensor that there is. And so this activity, this actual building activity, I have cool little kits that I just pop out and here's what they need kind of thing. So it's really about organization initially. My class periods are only 47 minutes, so I made it fit in a 47-minute, the actual initial building of the conductivity meter and the initial setup, and then the next day I walked in with the standard concentrations and then with an unknown, and so they already had their build from the day before. So it took me two 47-minute class periods, but you know, conductivity is not a huge standard in NGSS, but for me it was more about the science and engineering practices versus conductivity being the key point in that one. So it took me about two 47-minute class periods.
Thanks, Stacy. And the next two questions, maybe Fred can answer better. Fred, we had a question from Leah, and she has a TI-84 Plus, not the CE. Can she still use the Innovator with the TI-84 Plus?
No, it needs to be with the CE model because it needs to have the USB capability to talk. So sorry, that doesn't work.
Gotcha. And then second question is from Becky. And if I understand her question correctly, I think Becky was wondering if there's ever going to be a chance for teachers to upload their own activities for Innovator or projects with Innovator, say, to one place like TI's website. I know they had done that in the past and years ago with Activities Exchange, but I didn't know if that was something they were going to do at some point with Innovator.
Yeah, that's a great idea. And we're very interested in getting teacher-developed ideas in a kind of a blog or a exchange type of area, and that's something that we're working on. presently we're working on trying to create some additional projects that will be in a blog space that teachers will be able to download and work, and then provide feedback on how well they worked, and kind of pedagogical ideas of how to use them more effectively and that sort of thing. But that's a work that is in progress right now. So it's good to hear her feedback that that's something that she'd be interested in, because it's something we're working on. Yes.
Thanks. And probably another question for Stacy from Pleasant View School. They're wondering, how many students per hub did you have working?
So my STEM club after school, it's like 2 to 1 hub. I have 8 hubs, and I can get it done in my classroom. The good part about it is that everybody has a handheld, and so everybody has a calculator, and the innovator actually will beep when your program is not working right. So it's kind of cool to hear, even though everybody went through the same programming and everybody wrote the same program, not all of them work. But everybody wants to try it. So I have 1 per group. I have lots of the other equipment and other materials with the breadboard and some of the cables and stuff. But it really works. It's not a big deal. It's just like having 8 hot plates in a science classroom. We make it work.
Thanks, Stacy. And then, Fred, just a follow-up question. You had answered Rhonda's question whether the hub could be used with the PC-only version of Nspire. And you had said, yes, the hub works with Nspire for PC. And I think Ray had asked, what about MacBook?
Or did Ray say, and it works with MacBook? So the answer is yes, it works with both MacBook and PC for Nspire. Yes, it works on both.
Great.
Mm-hmm.
So, Fred, I'm going to give you control back because I think you had a couple last-minute things.
Yeah, yes, great, thanks. Okay, so one of the questions was, what other types of projects are there? What Stacy shared with you tonight was a fairly techie level of STEM projects. And I think that she did a great job with integrating that into her chemistry curriculum, particularly appropriate for like an AP type of class. But what about middle school or people who don't want to get maybe that involved? Well, remember all of those grove sensors that I showed to you in the beginning? Those simply plug into those input and output ports of the hub, and then can be accessed in a similar way through the calculator and TI basic program. And some of the projects that we've been working on that we're going to get posted on the blog, and these are projects that if in fact you're interested in trying in your classroom, I would be glad to send you some information on that. If you're interested, we can talk to Mike and try to make that happen. But some of the ideas that we have kind of a car pet alarm where students investigate the physiology of animals and how temperature affects them, and then they're challenged to make an alarm for a car, kind of a smart car system that sets off an alarm and takes an action if a pet is in fact in the car and it's getting too hot. Another one is a smart water management system. This would be great for like an ecology class where students are challenged to try to use a limited resource such as water in an arid region more efficiently by kind of creating an optimum way of using the water based upon measurements of temperature, humidity, soil moisture, and light level. And then they get the opportunity to determine how do you water. Do you water in a rush or in small little soaking doses, or exactly how does that happen? Another one is kind of something maybe good for a physical science class where students are investigating alternative energy sources. In this one, the students use 2 light sensors, 2 of those external grove light sensors, along with a servo motor and a photovoltaic or a solar panel. And they make a device to hold that solar panel out of cardboard and tape or glue, and they mount it onto the servo, and then they use the 2 light level sensors to have the the photovoltaic panel track the sun to be more optimum in the use of energy. We've got something on mood rings, that's right. Don't throw those ties out, mood rings. Again, looking at human physiology and how temperature changes with different physiological stresses. There's another one for a physics class of building a brushless DC motor. The one that Stacy just mentioned, how clean is the water using conductivity. Have another one on building a colorimeter for chemistry. Some ideas on doing electrophoresis, as well as some separation of water, investigations of math and music using the speaker, investigating beats and chords and scales and that sort of thing. We have activities on building binary number displays, hexadecimal number displays. You can get some STEAM in there by investigating mixing colors and sounds. So there's a lot of different ideas for what we can do with this. So at this point, I'm going to turn this back over to Mike, and he's going to kind of do some housekeeping with you on your professional development. And I'd like to thank you for tuning in tonight and hope that I hear some of your ideas on using the Innovator for STEM projects. So, Mike?
Thanks so much, Fred.
Trying to pass that back over.
Got it.
You got it, good.
So as Fred had mentioned, I believe during the agenda tonight, we're excited to be giving away to one lucky winner a T-Cubed Summer Professional Development Conference Workshop registration. So we have over 50 different workshops that are being offered. I was talking with Stacy before we started, and she said there's actually a Path to STEM summer workshop, I believe near you, Stacy, in Louisiana. Anyway, I think there's over 50 different workshops that are offered across the United States. Stacy, it is near you in Louisiana, correct?
Yes, I'm actually hosting it at my school. I'm putting it on, yes.
Awesome. And again, if you're not in Louisiana, there are lots of other Path to STEM summer workshops that are being offered this summer. So please feel free to visit our website to learn more. But the lucky winner for tonight is Rhonda Carter. So Rhonda, congratulations. We'll be in touch over email in a couple of days. So we hope to see Rhonda as well as everyone else at a T-Cubed Summer Professional Development Workshop. To receive a certificate of attendance, click the link in the chat window. Give me 2 seconds. There we go. Click the link in the chat window. Also listed is a link for the documents that were used tonight. So especially the information that Stacy had gone through with all the specifics is listed in that documents folder, along with Fred had mentioned that we currently have 6 different skill builder activities, including the one that Stacy had demoed tonight. So those are all in that documents folder as well. If these links aren't working for you for some reason, don't worry, you'll automatically get a follow-up email in a couple days. And with that follow-up email, you'll get a link to the recording, a link to the certificate, and a link to the documents. Thanks so much, Fred and Stacy, for everything you shared tonight. We had some great questions, and I think a little bit of excitement was generated tonight. So thanks so much for everything you shared.
Thank you.
Again, thanks everyone for joining us, and we hope to see you back online next week. Have a great night.